In this video, we will split up the fraction 1 over s squared plus 1 times s minus 2 using partial fractions. Here, we can't factor s squared plus 1 using real numbers. So in this partial fraction decomposition, we'll look at how to handle a quadratic in the denominator. When we make this partial fraction split where one of the factors is quadratic, then we'll write 1 over s squared plus 1 times s minus 2 as a sum of two fractions where the denominators of our two fractions are s squared plus 1 and s minus 2, the two factors in the original fraction. The difference here is that the numerator of our term with s squared plus 1 in the denominator is going to be as plus b, whereas the numerator for our other term will be c, as in the other example we looked at. A good rule of thumb when doing a partial fraction decomposition is to have the numerator 1 degree less than our denominator. So in these two terms, our first term has a degree 2 denominator and a generic degree 1 or linear polynomial in the numerator. In our second term, the degree in the denominator is 1, so in the numerator we have something degree 0, a constant. Once we set up this form, the way that we will proceed is the same way as when we had two linear terms in the denominator. In particular, we'll multiply both sides by that denominator. In this case, s squared plus 1 times s minus 2. Doing this, on the left, again we'll just have the numerator, 1. On the right-hand side, we'll need to distribute s squared plus 1 times s minus 2 to each of our terms, which gives us as plus b times s squared plus 1 times s minus 2 over s squared plus 1, plus c times s squared plus 1 times s minus 2, all divided by s minus 2. And like before, we're going to get some cancellations. In the first term, s squared plus 1 divided by s squared plus 1 is just 1. And in the second term, s minus 2 divided by s minus 2 is also just 1. So this leaves us with as plus b times s minus 2 in our first term, plus c times s squared plus 1 in the second term. Tying this all together, we're left with the equation 1 equals as plus b times s minus 2 plus c times s squared plus 1. And distributing here gives us on the right as times s, which is as squared, plus b times s, plus as times negative 2, or minus 2as, plus b times negative 2, or minus 2b. In the second term, we have c times s squared plus c times 1. And remember, this is all equal to 1 on the left-hand side. Combining like terms on the right, we want to look at what our coefficient is for s squared, s, and the constant. For s squared, we have as squared plus cs squared. Our coefficient of s comes from bs minus 2as, and our constant comes from minus 2b plus c. Combining these like terms, we have a plus c times s squared plus b minus 2a times s minus 2b plus c. And lining up coefficients in each power of s from the equation 1 equals a plus c s squared plus b minus 2as minus 2b plus c gives us that a plus c is 0, since our coefficient of s squared on the left is 0 and our coefficient of s squared on the right is a plus c. b minus 2a equals 0, since the coefficient of s on the left is 0 and the coefficient of s on the right is b minus 2a. And finally, negative 2b plus c equals 1 by lining up the constants on both sides. This gives us a linear system of 3 equations and 3 unknowns. Solving this linear system gives us that a is negative 1/5, b is negative 2/5, and c is 1/5. We can plug these back into our initial decomposition to get that 1 over s squared plus 1 times s minus 2 can be written as negative 1/5 s plus negative 2/5 all over s squared plus 1 plus 1/5 over s minus 2.